Have you ever noticed how a good part of the North American coastline follows a circle? Or that South America is shaped like a triangle and a rectangle, which turn out to combine into a Fibonacci spiral? This landscape geometry is based on exact proportions of the Earth's circumference, on the deepest place on Earth, and, in a very precise way, on both the position and the size of the Large Hadron Collider at CERN. Consider a line running from the Great Pyramid going exactly through the center of the Large Hadron Collider. This line ends up passing within 1.3 kilometers of the Mount Carmel Center, better known as the site of the Waco siege. On this site, 76 people died on April 19, 1993, when their compound was burned after a 51-day standoff with the authorities. Waco is noteworthy along this CERN line because it is situated such that its precise location defines the center of the North American circle by being at an exact golden ratio point along the circle's radius, which is 2,160 nautical miles, or precisely 1/10 of the Earth's circumference. Creating an analog 2,160 nautical mile circle on the center of the Large Hadron Collider defines a bisector between North America and Europe. This continental bisector intersects with another great circle that runs down the east coast of South America and through the deepest part of O'Higgins San Martin Lake, which is the deepest in South America and the 5th deepest in the world. The other point defining this great circle is Challenger Deep, the deepest spot on Earth. Notice how it also passes very close to CERN. Taking a closer look at the Large Hadron Collider for a moment, we lay out a circle of 86,400 foot circumference centered on the Large Hadron Collider, and see that it passes through all 4 of the collision points along the accelerator where the massive detectors are located. We define a vesica Pisces by laying out the same sized circle passing through the center of the LHC and aligned with our Great Pyramid to Waco, Texas line. This geometry syncs up with a larger circle that nestles between the vesica Pisces and the Challenger Deep line we defined before looking closer at CERN. This circle has an exact circumference of 216 kilometers, which is continuing the fractal pattern from the continent-sized circles and the Large Hadron Collider circumference. To be clear, the circle is depicted as being exactly tangent to the line, but there's actually a few kilometers of play with this particular alignment. While the Challenger Deep end is anchored by a precise Wikipedia point, the O'Higgins San Martin end is a deep area and is not a point. The number 216 resonates across both terrestrial and celestial realms. The Earth's circumference, for example, is 21,600 nautical miles. We see that the Sun is 864,000 miles in diameter, and the Moon is 2,160 miles across. 864 is a multiple of 216. There are also 86,400 seconds in a day, reflecting the 2016 resonance into the temporal. Now, many have commented on how CERN's logo seems to contain 3 sixes. Perhaps that is true given that 6 times 6 times 6 equals 216. Following through, we see that a vesica Pisces of sorts is left once the 6s are taken away. Potent symbology, 666 coming from the vesica Pisces, considering that 666 is well known as the number of man. Again, extreme geography is playing into the mix, with Mont Blanc, the highest peak in Europe, being 7 kilometers from our world deep line. Zooming out, we can see how Europe and Africa follow our alignments and how the Challenger Deep line almost exactly separates Europe and Africa at the Strait of Gibraltar. The line passes within 4 kilometers of the African Pillar of Hercules. The intersection of the CERN/North America Vesca Pisces bisector and the Challenger Deep line define a precise location on the Earth from which we'll lay out the rest of the geometry in this video. The coastline of South America follows 3 great circles, each having a circumference of 21,600 nautical miles equal to that of the Earth. These 3 great circles form a wedge that is 1/8 of the world's circumference by 1/4 of the Earth's circumference. Notice how this lays out an equator along the north edge and a pole at the south apex. Bisect the wedge and define another perpendicular pole. Sweep out a line about this pole to the Ahu Akivi Moe on Easter Island. These 7 statues face sunset on each equinox and are the only astronomically precise ancient feature on the island. This alignment passes through the southern tip of South America and precisely past Cape Horn, the most southerly spot in South America. We'll sweep out another line around our east pole to the region where the circle rounds into the straight edge of Chile's east coast, thus completing a box around the top of South America. Now divide the top edge into a golden ratio, and by adding a circle, we see that the box is actually a golden rectangle in some sense. Copying this circle down, we'll create another golden section line. Sweeping out from the end of this to exactly 45 degrees, or 1/8 of 360 degrees, we see that the west coast of South America is aligned, and that we have another fractal of 216. Expanding this pattern implies a Fibonacci spiral. One final line that creates another golden ratio division provides the backbone on which the North and South America connector sits. Adding back in our North America circle with its CERN to Waco bisector, we see that this phi connector comes within 10.4 kilometers of where the CERN to Waco line intersects the circle. So one last line, if you recall the line we just drew connecting North America to South America at the phi division of the upper portion of South America. If you do one perpendicular to that, it goes right through the mouth of the Amazon and continues on to Stonehenge within 13.2 kilometers. So here we have Easter Island and Stonehenge playing a role in laying out, or however you want to put it, the South American continent. And it just, you know, from what I've seen in the research, this kind of thing, it just goes on and on and on. And so if you're interested, perhaps consider going to bedrockgeometry.com and signing up for the newsletter. And yeah, and I'll fire you some stuff, some secret stuff. So thanks for watching. I appreciate it.
Okay, hello. In this video, it's a follow-on from some previous ones where I discussed the connections between geometry, numbers, and time. Now, it might, for some people's minds, it might be easy at that point to say, well, it's just sort of syncs up nicely. It's, you know, got to do with base 10 and, you know, and a legacy from the imperial, and it's not really meaningful. Well, I'm going to show you now how the modern meter and the imperial system goes back to no less than the building of the Great Pyramid, which is usually said to be 2500 BC. That's another story about the origin and date of it, but now we're also going to connect the esoteric with symbolisms such as used by the Knights of Malta, the Knights Templar, and how they connect. So essentially now what I've drawn here is a 24-pointed star, and in an earlier episode I pointed how the difference between the 12-pointed star creates the Maltese cross, but the Templar cross comes from the 24-pointed star, and I'll highlight that here. And this we're going to connect to the Great Pyramid of Giza, the most remarkable building ever built, and it was built at the dawn of time. History is false, it is ridiculously false, and the measurable facts are written in stone, while the academics argue over scraps of hieroglyphs. The actual data is recorded in the stone for all time. It can be measured, it can be tested, and it's there. They simply refuse to acknowledge it because it would destroy the existing paradigm of history, which is false. But here we have a stand. Now here we see the beginning of the Knights, the Templar cross, which appears from the 24-pointed star. 24 hours in a day is as old as Egypt. So, and not only that, you will find it in cultures across the world, how similar, referencing time in the same way, in the way that their calendars and the numbers in their calendars, the measurements of their temple, the numbers of statues, etc. of their temple will all come back to this geometry. And this is a very simple experiment you can do at home, and essentially we're going to make a clock with a piece of string, and where are we? Sorry, pardon me, I've extended. So we have the Templar cross emerging from the 24-pointed star. And here is the beginning of the geometry and a series of connections which cannot be, they can be maybe ignored by some, but they can be tested, and the implications are massive. So we see now the 24-pointed star, and I'm going to have to remove the camera, so I'm going to be a little bit shaky for a moment. Okay, now here we look back. So here we see the Templar cross emerging from the 24-pointed star. The Templar cross, let me see if you see, okay, we should focus in. Okay, so we see the Templar cross creates a 30-degree arc. That's 1800 seconds of a compass, sorry, 1800 minutes of the compass, or 108,000 seconds. 108, there you go, that's to start. But what I have now here is a 1 meter ruler. Okay, so the 1 meter ruler, people will say that well, because it's written in Wikipedia, but the meter is a relatively new measurement. I would say that this is nonsense, because this will now connect the Old Kingdom royal cubit, the Great Pyramid, which is the recognised Old Kingdom measurement, which is Petri and others as the base unit of the Great Pyramid. So we have 1 meter from the centre of the star. Okay, 1 meter from the centre of the star, and here we see how 1 meter forms this arc. So essentially what I've done is you would draw a large circle around this, and the circle has a 1 meter radius. Now if that 30-degree arc created by the Templar cross, which is 108,000 seconds, is pi over 6 or 0.52359 dot dot. So we're just going to simplify that to 0.5236. The ancient Egyptian royal cubit was 0.5236 meters. So pi over 6 meters equals 1 Egyptian royal cubit, and very conveniently that section of the arc is equal to 0.5236 radian. And so 1 Egyptian royal cubit is, as I'm going to show you now, is equal to a 1 second frequency. We're going to make a pendulum. Essentially, we're going to make a clock, and we're going to connect the allegedly modern meter with the ancient Egyptian royal cubit and show how the Great Pyramid is scaled to Earth and to time and to the meter through this very, very simple geometry in a very, very simple way. Okay, now this is an earlier prototype, but it's essentially, this is the same construction that I drew with built on the 24-pointed star, creating a 30-degree arc, and that section of arc is 0.5236 meters. So now I'll have it and a pendulum. So the center of gravity of this so the center of weight of the pendulum is the important point, and we have the to where I've tethered it. So from the central point to the center of gravity of this pendulum is exactly 1 meter. Now let's look what happened. Mersann's, forget the exact date. The early meter was defined by a 1 second swing of a pendulum. If you do a search, you'll find that they have it slightly less than a meter, but you need to remember that that's at standard gravity. Because the Earth is a globe and it's spinning, the gravity is slightly more at the equator than what it is at the pole. So as we move from the equator or back towards it, the gravity will change, and effectively will change the way that this pendulum acts. But so we've created this 30-degree arc, and now here's a very interesting thing, how the meter connects to the second. As long as I don't swing this arc more than 30 degrees, so get it out there, and let's let it swing. What's happening now is that if you time this, we have a 1 second frequency. So for 1 second, 1 second, 1 second, 1 second, it's going. This is a super, not in the age of atomic clock, super accurate might be a bit of a stretch, but this is a very, very accurate clock, and this system was essentially, well, this is where from our electronics, before the electronic age, we had to do things differently, and the young people probably have lost sight of that. But here we have a 1 second clock. Here's the interesting point. So it has a 1 second frequency, which means theoretically, because eventually we'll lose momentum, but per day this will create 86,400 per 24-hour period. So 1 meter creates a 1 meter pendulum, as long as it isn't swung outside of this arc, which is 0.5236 meters, pi over 6 meters, which that arc is 0.5236 radian, coincidentally, and that arc is also 1 Egyptian royal cubit. So 1 second equals 1 meter equals pi over 6, or 1 Egyptian royal cubit, and 5.236 radian. Radian is, we usually work on 360 degrees. Radian divides the circle essentially into 2 pi. But if this isn't interesting enough, 86,400 400, that's the frequency. Multiply the maximum. So let's now jump over. We're standing in front of the Great Pyramid of Giza, and we're standing at a corner of the Great Pyramid. So we don't just see one base, we see two bases. So that's the most you can see. Standing at the corner is the maximum observable base length. So it's essentially, anyway, now we it's 756 feet each base. That's the pyramid itself, but the pyramid sits on top of something called the socle, or the paving stones, and at the corner of the pyramid there are something called the sockets. So the sockets will give the pyramid extra base width, and the socle gives the pyramids extra height. So we're not working off the pyramid, we're working off the Great Pyramid and the whole, not just the pyramidal shape, but also the structure on which upon it is built. Multiply the maximum visible base by 86,400, or the amount of seconds in a day, and you get the circumference of the Earth above 99.94%. The accuracy wasn't rivaled until the satellite age. 86,400 times the height of the pyramid, including the socle, gives us the polar diameter of the Earth. Again, to a level that it wasn't rivaled until the satellite age. So 86,400 seconds per day on a 1 meter pendulum at 108,000 seconds arc, which is 1 Egyptian royal cubit, pi over 6 meters, pi over 6 radian. Now back to geometry. If I was to make a cube and put a sphere inside the cube, the ratio of volume between them would be 1 to 1.05236. So this is also a cube being a hexagon in a three-dimensional, two-dimensional, a hexagon with a circle inside. And so anyway, 1 meter equals 1 second, 108, 1 Egyptian royal cubit, pi over 6 radian, pi over 6 meters again, 86,400 frequency, multiply Great Pyramid of Giza by 86,400, multiply the height, you get the polar diameter of the Earth, multiply the maximum visible base, you get the circumference of the Earth. Now, I very much respect Randall Carlson, Scott Onstott, and Graham Hancock, but I dispute that 432 is the sacred number of the Great, or 43,200. It's 86,400, because this is a much more elegant way of doing it. The 43,200 method gets a bit messy because you have to use a bird's eye view and then multiply it by 2 and stuff. If I stand at the corner of a pyramid, I get the maximum visible base and I get the maximum visible height. From that one position, I multiply the height or the base by 86,400 and I get the dimensions of the Earth. So my mind blew when I come across this. This you can test it at home, test it, do it. This is the beauty of the geometry and the measurements. It can be. You draw a vesica, you make a hexagon, and the world is yours.
The square-based pyramid in 6 easy steps. This is an activity that is tailored to suit Oswell's curriculum area, Mathematics Level 6, Measurement and Geometry, talking about shape. In this lesson, students will be able to construct an origami square-based pyramid and consider its features in terms of volume and surface area. In an activity following the folding of origami, students will explore the diversity of pyramids across history by comparing their pyramid to those found in China, Korea and Indonesia. The assembly and demonstration of this activity provides a good rehearsal for the language of geometry, as there are different parts of the shapes being referred to, or Booker's formal geometric language can be discussed here. let's get on with this. Origami is good practice for what Booker outlines as spatial awareness as well. So we need to square a piece of paper, and then we prepare for a base fold. So fold the square into a right-angled triangle, an isosceles triangle, open it up and do it again. So here we can notice that the paper was divided into halves, and now we see quarters. Execute a base fold like so. And notice we have a triangle that is 1/4 the size of the original piece of paper. And fold the bottom points of the triangle and bring them to the apex. And you do this with each corner. Now the base fold is a tricky step, and to sort this out you use the student experts that will emerge and encourage them to help each other and follow the procedure step by step. This is a good example of kind of geometric reasoning taking place, and spatial awareness is critical according to Booker in real-world competencies, and mentions the flat pack furniture as a geometric reasoning task. This piece of paper looks like a square. How small is it compared to the original square? That's a fraction that the kids can work out. So you fold the corners in to the line of symmetry, which is in here, and you do this for each outside corner. Now some kids will refuse origami, so the solution is, while the students are encouraged to try the origami, some might struggle. So this lesson can be differentiated with explorations of other pyramids using paper nets and glue, all bolster the drawing and making of models and thinking logically. So you should have other pyramid nets to cut out and glue and to assemble. Here you can provide square-based pyramids, triangle-based pyramids, etc. They can all be used in the next phase of the activity. So you unfold from this step, from the kite to the main triangle, almost. Fold the tip over the end and return along the folds to the line of symmetry. Assuming you're in a class with children that have iPads or similar ICT, after they've built their pyramid, get them to take a photo of their pyramid on a reasonably plain background so they can crop it out, and have them creatively stick their pyramid next to a pyramid found in China, Korea, or Indonesia. Here they can compare how it's different, so we might look at the volume of their pyramid that they've made and compare it to the volume of a pyramid in China, say. So once those have all been folded in, you open the triangle, or open this square rather, so the edges are all at right angles, and then you put the long edge of the kite on the table and press down gently while drawing out the edges. And again, if this step's a bit tricky, you can either help the kids or have them help each other. And for those kids that have used nets as well, they can photograph theirs and put it in to a picture with another pyramid and do the comparison stage as well. And there you have it. You should have, perhaps on the section you've cut out, questions to ask about your pyramid. So this is where we apply the geometric concepts and knowledge that draw from what children should already know regarding area, perimeter, measurement. They can describe their pyramid, they can estimate their surface area. Centimetres are probably an appropriate unit of measurement for this sort of thing. And they can make a poster on their iPad or what have you, but as an optional last phase you can smash it.
Today we will talk about graphs that can be generated by multiplications tables in the movement of planets in the solar system. On internet, there are a number of blog and videos which show graphics that can be obtained from the tables. The principle is, you draw a circle. Then on this circle, you draw points. We will consider endpoints that can score from 0 to n-1. The principle is that we connect each point by its multiple modulo the number of points. If I take the table of 2 for 100 points, then, we have the following correspondences. 1 is connected to the 2. 2 with 4. Then, 3 with 6, and so on. 49 is connected to the 98, 50. As we begin to 0, we don't connect to the 100, but to 0. The 51 it is connected to 2, because the rest of the division of 102 by 100 is 2. You can see the graphic that we obtained. I'll take some examples of bases that can be found on the internet. Take the table 1. For 10 points, that's what you get. Now for 12, 13, and so on. For the table 1, we can observe regular polygons. Let the table of 2, 4, 1.2, 3, and so on. There appears a kind of heart. Mathematically, this is called a cardioid. Let's go to the table of 3, 4, 1.2, 3, and so on. Now there are 2 loops that appear. Watch what happens to the table 4. 3 loops appear. Now look for the higher tables. A conjecture appears. The multiplier least 1 corresponds to the number of loops is formed. So far we have looked at the tables around the numbers. But look what happens when we consider the non-integer number table. For example, the table 1.5, and so on. Look at the table 1.88 and 1.62. We will return to it in a few moments. One could view this type of graphic in another way. Indeed, consider 2 points which run on a different circle, and are connecting the dots. These 2 points have different speed. Finally, by approximating the orbits of the planets in these circles, even if their orbits are ellipses with a very low eccentricity, we can model the movement of planets in the solar system, giving movement speed corresponding to the period of rotation around the Sunday. Take for example the heliocentric movement in the repository, the Sun in the center, the orbit of the Earth and Mars. The Earth takes 365.25 days to circle the Sun. Mars puts 687 days. The rounded report period is 1.88. Now look what happens. We see not only show the graph in table 1.88. It is also a Q changes appear the Mars trajectory in the terrestrial reference frame. Now look what happens if we consider the orbit of the Earth and Venus. Venus puts 225 days to rotate around the Sun. The report periods is 1.62. What happens to you between Mars and Venus? The report periods is almost 3. The graph obtained substantially similar to that of the table 3. Despite the large number of neglected factor to simplify modeling, like multiplication tables, the movement of planets hidden through his dance in space, a certain artistic side. Here. I hope you liked this video.
Hello and welcome to this video in which I hope to contribute something to the flat earth debate with the help of this inspirational lady, Dame Ellen MacArthur, who in 2005 set a new world speed record for single-handedly circumnavigating the globe, which is the global version of it, although I never really bought into the hype about it, because when you look at the map of where she sailed, and this is the only one I can find on the internet nowadays, you can see that she set off from Britain, she sailed past Africa and around Antarctica, back again, which on this map looks okay until you consider that Antarctica is the narrowest part at the bottom of the globe. It's not the same as sailing around the equator, which is what I'm sure most people would think of as circumnavigation. She set off from Britain, sailed through the Atlantic, to Antarctica, which you can't see on this map, and back again. Now, it's quite a long way, but it's not circumnavigation. If she'd come around the equator, then she would have crossed the vast expanse of the Pacific. If you look down at the bottom of this globe, you can just make out Antarctica. But to sail around that bit there is never going to be the equivalent of sailing around the Pacific. And that's not even the whole Pacific. If you look at Hawaii just there, if you were to swivel it around, there's Hawaii. So you've still got all of this Pacific to go, even if you take a shortcut through the Panama Canal and then around the Atlantic, which would be fine. That would be circumnavigation. It wouldn't be setting off from here, coming down the Atlantic, around the Antarctic and back again, which, as I say, is a long way, but it's just not circumnavigation. Even if you call your autobiography Full Circle, it doesn't make it a circle. It's an odd teardrop shape down the side of the planet. So I've always been underwhelmed by the whole MacArthur thing, until just recently when I've seen these videos on YouTube about the flat Earth, and they keep showing this map, the azimuthal equidistant projection, and as soon as I saw that, I immediately thought of Ellen MacArthur, because if the Antarctic is this edge around the disk, and if she did sail around Antarctica, then she clearly did circumnavigate the Earth. And if the powers that be know that we live on a disk like this, then you can understand why they heaped so many awards upon her. She was given, she's been made a dame. Here she is receiving it from the richest human being that ever lived, whose name isn't Rothschild. There she is with the medal, and she received France's highest award as well, and plenty of other awards. She became a household name in the UK. So obviously someone puts a lot of store in what she did. So let's just imagine that we do live on a disk and that she did sail around the edge, and let's visualize that. If we say that she set off from Britain here and she sailed around Africa and around Antarctica, and this is rough because I'm using a trackball for this, we'll assume she didn't weave about so much, and we'll assume that she didn't take a shortcut across the Pacific and that she went all the way around here. Now it's not a circle, we've got this section here to account for, and we could work out the area of this with calculus, but since she started and finished from the same point, and since everything inside this journey is the habitable area available to us, let's just take it at face value and say that this was a circular journey, and use that to work out the area of this disk that we may or may not be on. So if we take the full circle, we need to know the circumference of the circle. We need to know the length of the journey. So we go to the font of all truth, Wikipedia, and we scroll down to her racing career, and here it is. The circumnavigation took 71.5 days, and it was 50,660 kilometres. So that's 50,660 kilometres was the circumference of the circle that she sailed. And if we know the radius of that circle, then we can work out the area. And we can work out the radius because we know the circumference, which was 50,660 kilometres. So let's get the calculator. 50,660 kilometres circumference, and we need to divide it by 2 pi. So over 2 times pi gives us a radius of 8,063 kilometres. So now that we've got that, we can go back to the area calculation, and it's pi r squared. So this is the radius, we square that, multiply by pi, and that gives us an area of 204,230,456 square kilometres. So how does that compare with the official size of the globe Earth? Go back to Wikipedia, scroll down to the size, and here we are, surface area 510,072,000 square kilometres, compared with what we just came up with, 204,230,000. This is less than half the official size of the globe. So it's a pretty rough and ready calculation. So I'm putting this out there for the big boys to have a look at. The flat earthers and the flat earth rebutters. People with more resources and more brain power with me should be able to use numbers like the length of journeys that people take when they say that they've circumnavigated the Earth, and you should be able to work out from that the actual physical size of either the disk or the globe that we live on. I don't think there's any conclusive proof either way, but at least this gives people something to work with. So that is for you guys to look at, really. But as an appendix, I just want to show you what Ellen MacArthur is up to these days, because she's retired from competitive sailing and she now has the Ellen MacArthur Foundation, and as you can see, their mission is to accelerate the transition to a circular economy. And this is a glorified way of talking about recycling. It's just that you should use resources in such a way that you can reuse them endlessly, in theory, and keep putting them back into the system. So circular economy sort of seems a bit of a coincidence. And then when you look at the logo, 3 circles arranged in such a way that these 2 circles look a bit like a tube. So there's a tube coming through the outer circle, a three-dimensional circumpunct, an eccentric quasi-vulvic totem, looks like to me. So, and then just look at the circular economy overview. Everything circles, circles within circles. I don't know if that's telling us something, but circles do seem to play a large part in Ellen MacArthur's life these days. So there you go, professional flat earthers, see if you can do anything with this. And then just as one last word for people like Ellen MacArthur that are into the environment, if you want to do something about the environment, then recycling is one thing, but I think you really should start here. Do something about this, because I'm sick of looking up in the sky and seeing that every day, and I don't need some do-gooder telling me that I need to recycle in order for this to stop. So there you go, take what you can from it. Good luck with your calculations, everybody. Thanks for listening, and goodbye.
Celestial mechanics is the field of astronomy dealing with the motion of celestial objects. While celestial mechanics has its roots in ancient times, and in particular ancient Greece, the beginning of our modern understanding of it only goes back about 500 years. However, celestial mechanics is the basis of spaceflight, which has really opened up our understanding of the universe. Ptolemy was a Greco-Roman philosopher of Alexandria. He was born in 90 AD, and he died in 168 AD. He was known for his geocentric cosmology. Here is a video animation of Ptolemy's geocentric cosmology. Note that there are only 5 planets. That's because Mercury, Venus, Mars, Jupiter, and Saturn are the only planets visible to the naked eye. Here is an illustration of the Ptolemaic astronomy basic elements. It involves a planet rotating on an epicycle, which in turn rotates inside of a crystalline sphere that has this Earth slightly off center of that crystalline sphere. Ptolemy saw the stars as being in the outermost crystalline sphere. This system is an excellent example of a philosophy-driven model that needed substantial additional elements to make it fit reality. Nicholas Copernicus was the Renaissance mathematician and astronomer who developed the heliocentric model of the universe. It put the sun at the center rather than the earth. Copernicus was born on February 19, 1473, and he died May 24, 1543. Here is a video animation of Copernicus's heliocentric cosmology. Note that there are only 5 planets. That is because Mercury, Venus, Mars, Jupiter, and Saturn are the only planets that can be seen with the naked eye. Galileo was an Italian physicist, mathematician, astronomer, and philosopher. He was born on February 15, 1564, and he died January 8, 1642. Galileo was an early champion of heliocentrism. He was the first known astronomer to use a telescope. As a result, he discovered the 4 largest moons of Jupiter: Callisto, Europa, Ganymede, and Io. Hence, they are referred to as the Galilean moons. The biggest myth about Galileo is about his trouble with the Catholic Church. The myth is that he was prosecuted for teaching heliocentrism in opposition to the Bible. This myth is false and originated with the 19th century anti-Christian bigots William Draper and Dixon White. They tried to portray it as science versus the Bible. In reality, it was science versus science. Specifically, Ptolemy versus Copernicus, because Ptolemy was seen as an authority by the scientific establishment of Galileo's day. Also, in one of his books, Galileo had made the Pope look like a buffoon, thus belittling the Pope's office and authority. And this was all happening in Italy at the height of the Protestant Reformation. Galileo's first trial was in 1616. The Pope's authority over Europe was falling apart, and Galileo was yet another challenge to his authority. It needs to be noted that the proponents of heliocentrism in Protestant countries, such as Kepler, had no problems from Protestant churches on this issue. Galileo's work helped pave the way for further development. Kepler's discovery that planets orbit the sun in an ellipse, and Newton's development of the concept of gravity. Tycho was born December 14, 1546. And he died October 24, 1601. He is well known for his accurate astronomical and planetary observations. He is also known for his hybrid geocentric-heliocentric model. Here is a video illustration of Tycho's hybrid geocentric-heliocentric model. Tycho's cosmology was essentially geocentric, in that everything ultimately went around the Earth. However, it was part heliocentric in that the other planets were seen as going around the Sun, while the Sun went around the Earth. In fact, a modified version of Tycho's model is held to by modern geocentrics. However, despite the fact that heliocentricity is taught as fact in schools, it is not absolutely true. This is because the real answer is that according to general relativity, both geocentricity and heliocentricity can be considered correct. This is because according to general relativity, you can choose any frame of reference you want because they are all valid. However, this does not include only geocentricity and heliocentricity, but Mars centricity, Venus centricity, and even Kepler 62f centricity. It is simply a matter of choosing the most convenient frame of reference. Johannes Kepler was a German astronomer and mathematician. Kepler was born on December 27, 1571, and he died on November 15, 1630. He is best known for his laws of planetary motion. Kepler's laws were derived by use of the data collected by Tycho Brahe. These laws were for planetary motion around the Sun. However, they applied to dwarf planets, asteroid, moons, and satellite orbits as well. Kepler's first law is that all planets move in elliptical orbits with the Sun at one focus. This was actually a departure from the original idea that planets moved in circular orbits. Kepler's second law is that a line that connects a planet to the Sun sweeps out equal areas in equal times. That is, when the planet is closer to the Sun, it moves faster, and when it is farther away from the Sun, it moves slower. Kepler's third law is that the square of a planet's period is proportional to the cube of the semi-major axis of its orbit. Isaac Newton was an English physicist and mathematician. He was born on January 4, 1643, and he died on March 31, 1727. Newton is considered one of the most influential scientists of all time. Newton developed the mathematics of calculus, which helped him develop the basic laws of motion. It also helped him develop his most famous work, the law of gravity. All three of these paved the way for a full understanding of celestial mechanics by not just describing how moons and planets move, but why they move the way they do. Orbital mechanics is the physics that describes the orbits of satellites and planetary bodies. It is ultimately based on Kepler's and Newton's laws. It is used to determine future positions of planets, moons, man-made objects, and any other object in space. Here are the main elements of orbital motion. R is the radius of motion from the center of mass of the gravitating body. G is the gravitational acceleration. V is the velocity of the satellite. And theta is the angle of the velocity to the radius. Planetary motion is a special case of orbital motion. It obeys Kepler's and Newton's laws of motion. However, planets are large enough to have significant gravitational influence on each other. As a result, only some orbits in a planetary system are stable. The main motion of a star as seen from the Earth is called its proper motion. A star's proper motion is the angle the star moves across the sky over time due to its motion relative to the Sun. It is a function of the star's distance and transverse velocity. The radial velocity is found by way of the star's Doppler shift. The transverse and radial velocity combine to give the star's space velocity, which is its actual velocity relative to the Sun. The motion of stars relative to each other are essentially random. While gravity between stars does affect this motion, it is small but acts over a long period of time. However, the same main elements apply to stellar motion as does to orbital motion. The same basic laws of physics apply to galactic rotation as does any other orbital motion. However, galaxies are more complex than planetary systems, and so exhibit different velocity versus distance curves. The lack of sufficient mass to explain galactic rotation curves has led to the theoretical idea called dark matter. While often considered an exotic form of matter, it could still be some type of undetected normal matter, such as rogue planets. Celestial mechanics is the study of the motion of heavenly bodies. Ultimately, it deals with orbits of one sort or another. However, understanding orbital mechanics is what allows spacecraft to orbit the Earth as well as travel between planets.